This work was done with several collaborators, one of whom is in the audience, Edwin Huang. One of the first talks I gave on this was actually a Zoom talk here at the KITP, and this work came out 3 years ago, and we've been working on it since then. But I was getting kind of bored with it until I opened the web one day and I saw this paper. And an interesting title. It says it's proposing a correlated BCS wave function for unconventional superconductors. And then it stated lots of interesting things, like the quasiparticles are non-BCS. There's asymmetry, particle hole asymmetry. And I said, what's this wave function? So here's the wave function. And I said, wait a minute. That's the wave function we wrote down here. And it's exactly the same thing. So then I decided, I think I need to start talking about this again. So why would you ever write down such a wave function? Because there are three variational parameters here. Okay, so why? Okay, now there's a way in which a wave function with these three variational parameters is sort of trivial. We know BCS, the wave function looks like this. This pointer is not very good because there are only two occupancies in the normal state, 0 or 2. But if you just write this as a product over the positive values of k, then it naturally takes on this form, but the coefficient here of the singly occupied part and the doubly occupied are related. Okay, so if you go to this form, if this is supposedly describing the state of your system, and these are all independent, then you clearly are not describing your ground state. I mean, your normal state is not that of a Fermi-liquid. The correlations are inducing occupancies which depend on the momentum, which are different from 0 or 2. And right, so that's not right. And if this is at all non-trivial, it has to be controlled by a fixed point, and that's really what the whole talk is about. Isolating the fixed point that gives rise to this new wave function as a wave function for unconventional superconductivity, which is what we've been working on. So just to review, Fermi-liquid theory is a fixed point in the sense that all local interactions, if you work in the thermodynamic limit, they're either marginal or they're irrelevant. The chemical potential scale is thus to the -1. But if you go and calculate this to one loop order, the beta function, all local interactions that are positives renormalize to 0. The only thing which is relevant is the BCS channel or a CDW. Okay, so if you're thinking now, so the question I want to ask is there an operator that one can write down which has a scaling dimension less than -1, so it's more relevant than the chemical potential? And if so, it would be a relevant distortion of a Fermi-liquid. And does such an operator exist? Okay, this is, I think, the physical motivation to this paper that Anderson and Haldane wrote back in 2000 when they were trying to understand the stability of Fermi-liquids. And they wrote it in this way, so you have left and right are completely, there's time reversal symmetry. What the whole point is that if you're trying to look at what the general group is for a Fermi-liquid, it's really O4, because there are 4 objects that get rotated into one another. And these 4 objects either have proper or improper rotations. If it's a proper rotation, then you don't change anything. And that's the determinant which rotates these 4 objects is equal to 1 of the matrix is 1. And this is SO4, which is just the 2 SU2s associated with the charge in the spin sector, which are clearly equivalent to one another in a Fermi-liquid. And then the improper rotations in which the determinant is equal to -1. And this is just the quotient of O4 with SO4, which is just Z2. Okay, so their point is that there's an extra Z2 symmetry in a Fermi-liquid. So what is that symmetry? Okay, and this paper, interestingly enough, before we started working on it, had only 3 citations. Everyone seems to have forgotten about this. But the paper is very interesting. Okay, so here's my 4 component spinner. To make the rotation that I want evident, I just want to go and represent this in the Majorana basis. So I'm taking sums and differences, so I have symmetric and asymmetric components. Okay, now it's clear what the improper rotations do. The improper rotations have a determinant of -1. The simplest one is just this, 1 minus 1 along the diagonal, and that operating on this is just interchanging these 2 components. So it's a particle-hole transformation. So, as you well know, Fermi-liquids have this inherent particle-hole symmetry. And if you violate this, you can't be describing a Fermi-liquid. So what does it mean for a Fermi-liquid to have this symmetry? Okay, so it's just a particle-hole transformation. Okay, if you write out the Fermi surface, EP equals EF, remember the Hamiltonian is EP minus EF, NP sigma. The Hamiltonian is equal to 0, which means for electrons at the chemical potential, there is an extra symmetry. Namely, I can do this symmetry with this transformation with impunity, not changing anything about this one. Okay? So their whole point is that Fermi liquids have an extra symmetry in them. Okay. And this is only for electrons right at the Fermi surface, and this is the Z2 symmetry. So how do you destroy a Fermi liquid? The simplest way is just to destroy, well, everything that has to destroy this Z2 right at the chemical potential. Okay, so what could you add here to destroy the Fermi liquid, or the Z2 symmetry, even when EP is equal to EF? We have to add a term that is odd under this transformation. The simplest term that you can add is this. Okay, and this is odd under Z2. And interestingly enough, this term has a scaling dimension which is -2. It's just one momentum integral. And if you are assuming the Fermi liquid part is the relevant part, then it's just governed by the scaling dimension of the fermion operators to the 4th power, which is just -2. So it's a relevant perturbation. You cannot end up with a Fermi liquid. And so there has to be a new fixed point. Okay, this is the Hatsugai-Komoto model. And since all you're doing is having a U, every time you put 2 electrons into the same momentum state, if U is bigger than the bandwidth, you must have an insulator, because you then pushed the doubly occupied band up. Okay, so this model is an exactly solvable model. It's solvable for a Mott transition, and this is what the green function looks like. The green function is just a sum of 2 poles. And these poles have a weight which is not given by anything fermionic. These are composite excitations here, and their commutation relations are non-trivial. Okay, so if you have a sum of 2 poles, one locus of poles lies here, the other one lies at this quantity, and this is equal to 0. Okay, so this is the lower Hubbard band, this is the upper Hubbard band. So your green function is sum of 2 quantities. Sum of 2 quantities can equal 0, which means you have zeros. Every time you have zeros, you have to worry about this thing that is very popular, the Luttinger count. So let me recast the Luttinger count in the following way.
Philip, sorry, quick question. In your form of the Hamiltonian, does it mean that the momentum transfer is 0?
Yeah, right.
So it's the interaction of infinite radius in real space.
Yeah, absolutely. Right. It is, absolutely. The only way to get this is an infinite range interaction.
Why can't we gauge it out in this
Why can't we what?
Why can't we gauge it out?
Why can't we what?
Why can't we gauge it away?
I don't see how you're going to do that. It's the only relevant perturbation.
It's a constant in real space, right?
No, but it depends on the center of mass of all pairs, regardless of how far they are away. It does not go away. Yes?
If I take almost your case, interaction which is almost constant in real space. Sorry. If I take your case, interaction that's almost constant in real space, but still at very large distances, it will eventually go down. So what will happen?
I don't know exactly what will happen in that case. In that case, I think I know what will happen. There will be an extra moment if you were to Fourier transform that, there will be at least two momenta involved.
Mm-hmm.
In that case, that one would be marginal.
But will you stay?
No. That term is less relevant than this one. Because this has scaling dimension -2. You can't get any better than that. Okay. So let me go on to this recasting of the Luttinger count. Okay, if we have u equals 0, we only have one pole. And we know everything about that. But let's think about the Luttinger, let's think about how we would interpret the thing that goes into the Luttinger count. Okay, so if I have this loop this Fermi surface, I can locate it by putting a loop around it. And remember now, this is the omega 0 component of the green function, so it's a loop in the complex plane, but omega equals 0. This loop, you can then calculate the weight in this loop, which is just ultimately given by the phase of the green function, which is just this quantity right here. This trace G partial G inverse is just the phase integrated around this loop. And this has to be 1. Okay? Okay, so that's how you can think about, and the thing that you view as Luttinger's theorem is just this quantity. But I want to recast it in a completely different way. Okay, now consider the case that we have. For any finite value of u, you will have two poles, and they'll be slightly split apart. Okay, this is now the lower Hubbard band, this is the upper Hubbard band. And the width of the upper Hubbard band is smaller because it's epsilon plus u equals 0, which means in momentum space it has to shrink. Okay, so now, if you assume you have adiabatic continuity between this and this case, then I can put a loop around this. And the key thing about the stability of Fermi liquids is that I can make this loop as large as I want, and I don't encounter any instability in the system. There are no singularities. Okay, now if I assume that this is completely adiabatically connected to this case, I have to get for this invariant 1. But there's another way of doing this. So this assumes that there is no singularity. But I could have done this another way. I have two circles right here. I could have formed a loop around each of them, a loop around this one, and if I do that, I would have obtained that n1 is equal to 2. So there's clearly a problem here. The problem is that you assume there's no singularity in going from here to here. The problem is you can't form these two surfaces without some sort of singularity in the problem. There has to be a surface of zeros separating the lower band and the upper band. And the moment you do that, you can't make the circle as large as you want. You have to take into consideration the singularity that you will encounter from this circle going into the zeros, which means you're changing the topology. If you change the topology, then the correct way then is n1 is 1 plus 1 minus 1, and then you end up with 1. Okay, so and here is, and if you then go to the case where you only have one surface, The zeros are now pushed all the way up. You can make this as large as you want, nothing happens. This thing is equal to 1. Now note, this thing is either 1 or minus 1. Okay. Now, my point is, this is counting the homotopy charge, or if you want the K-theory charge. It's not counting the physical charge. And the whole point here is that Luttinger's theorem, if there is such a theorem, is entirely about the homotopy or the K-theory charge, not the physical charge. Okay, and this is why, if you evaluate that quantity for any number of interacting models, here it is for the HK model, n equals 1 is what you would get for a system in which the Luttinger count is equal to the number of particles. You'd only see this region right here. We're seeing all sorts of different colors right here, which means in general you have a violation of this Luttinger count. And it's not just in this HK model. Okay, it's in Hubbard models. Here it is in this. Okay, so I have to speed up. Okay, so my first part is the Luttinger's theorem, I think, is a misnomer. It is counting the K-theory charge, not the physical charge in the system. And if you don't like the fact that this model is, because it has a singly occupied region, is hugely degenerate, you can make it you can get rid of the degeneracy entirely, as shown in this very nice paper, and you still have the zeros. As long as you have the zeros, the mechanism you use to get the zeros doesn't matter. And you can easily show that, in fact, there are no local perturbations that are relevant relative to HK. They all scale to 0. They all scale to 0. And hence, this really is a fixed point. Okay, so here we are. Now, the thing I want to ask is, what about superconductivity? Okay, which is how we really started this. If you just add on this term to HK and redo the Cooper instability argument, since this starts off as its life as a doped Mott insulator, you'll be doing the analog of the Fermi-liquid problem for the doped Mott insulator. Okay, and if you add this term, what is the sign of this? This thing is in fact negative. Okay? So there is a Cooper instability. And Edwin was the first to show that in fact you can calculate the superconducting instability exactly in this model, and it diverges when this denominator is equal to 0, and you can show that and that will define TC. And as you see, this thing grows as it does in a Fermi-liquid, and then you see that once it crosses here, that will define the divergence of the susceptibility, and hence that will define the TC for the transition. So we know the ground state is a superconductor. Okay, here's this. Okay, now the wave function. Since there are 3 kinds of occupancies in the ground state, in the normal state, we need a wave function that's 3 parameters in it. And that was what was written down, and I'm glad people are finding it useful. So this is, yeah, okay, so then you can use this to then go and find the stand.
B here is the Cooper pair operator.
B?
Yeah.
Yeah.
Okay. So it's 2 electrons, 4 electrons.
Yeah. That's okay. Right. So this is a gap equation. You can formulate that. You can compute the free energy exactly because it's an exactly solvable model, at least within the context of the wave function. You can see that it seems to be a first order transition. So it seems as if where you get the turn on of the gap is not where the susceptibility diverges. However, the minimum of this does seem to be exactly where the susceptibility diverges. Okay. Now, since we have the wave function, we need to know what are the excited states. So you can define the excited states by an operator that kills the superconducting state. And the superconducting state here is no longer a linear combination of particles and holes. It's the stuff that gives rise to the Mott insulator. And those have to be in terms of the operators which create the lower and the upper Hubbard bands. And these are composite excitations. And note, there are things, you can define two of these operators for both the lower and the upper band. Okay, and so my point now is you can calculate the spectral weight, and in fact, here it is. You form a gap both in the upper band and the lower band. Okay, 1 minute left. Okay, so this is nice because it says that although the system is in the superconducting state, a pure low energy property, it still knows about the high energy state. It still knows about Mottness. Okay, now this is has always been one of my major motivators because Dirk van der Merle's experiment showed that there's this color change. And the color change is that there's transfer of spectral weight from the 2 eV range down to below that the moment the system becomes superconducting. And we have the possibility of explaining this because we have a state that involves the high energy sector. Okay, and it's just a small change, so we just integrated this band right here as you turn on the BCS coupling, the Cooper instability term. And what we found is that this thing is bigger than 1, and it decreases rather as you crank up U over T. And U over T corrections are always this dynamical spectral weight transfer, which is patently absent from the HK model. That's the only difference between that and the Hubbard model. And okay, and it's roughly what you see in the experiments. Okay, I am out of time. The superfluid density you can also calculate, and it looks like this. So here's the Fermi-liquid result. Here's the BCS result. Sorry, here is the PYH result, or the superconducting conductivity in the HK model, and it is suppressed relative to what it is in the BCS case. Okay, there are lots of other properties you can go and calculate. Here's a list of all of them. Since we have the wave function, everything that was done in the BCS paper, we can go and do with this new wave function. And you'll see distinctly different properties over here for all of these things because of this Mott scale physics that's involved in the superconductivity. Okay, so this is my last transparency. If you're looking at this evolution from a Fermi gas to a superconductor, my point is that I think there's a terminus of this evolution, and it's Neville Mott. Okay.
I have two questions very quickly. First, I want to return back to what I asked you during your talk. You have interaction, which in real space is just have infinite range.
Yeah.
And have a special behavior. Question is this: suppose that interaction is cut at some large distances. Eventually, if you gradually reduce the scale at which interaction is cut, you go back to conventional behavior, and at small u you will not get anything. It will be conventional Fermi-liquid. So my question is this.
No, because if you go back to this, in other words, if you take the limit in which the range now goes back to just incredibly short range or Hubbard,
yes,
we can show that not even that is a relevant perturbation to this fixed point.
Wait a second. Then we go back to conventional short range interaction, and you are saying that new physics appears at infinitesimally small u. So I consider conventional theory with short range interaction with small u. And your point was that there are two poles appear in the green function,
right,
and zero in between it. I cannot imagine that it will
happen. Right. So then the key point is this interaction relevant?
Right,
okay?
That's what I'm asking.
And my point is that your interaction, which depends on the range, if you were to Fourier transform that, would have at least two momenta in it, which means I have not described that.
Right, but my question
Mine is just one momentum.
Sure, but my quick question is this. Is your case a limiting case when if I take any cutoff of the interaction, I go back to conventional behavior? or there is some range of real interactions that decay at large distances when your physics works already for small interactions?
I would say the answer to that question is yes, yes. The conventional thing would have to apply because anytime there's a cutoff, the power counting that I did doesn't work.
Yeah. Okay, and then second quick question for just 1 second answer. You have supposedly repulsive interaction.
Right.
Which is momentum independent.
Right.
What kind of superconductivity you get?
The Cooper term that I added is the standard Cooper interaction. So I have HK, just with repulsive interactions, and then I just did what Cooper did for Fermi-liquid, but now for the HK model. And then I end up with this weird superconductor that has these high energy scales. Other people have, in fact, put in a momentum dependence for the form factor, and they've gotten out D wave. I mean, it's not profound. The important thing is that there is a superconducting instability even for a Mott insulator, for a dope Mott insulator.
Yeah, when I look at the Hamiltonian that you wrote, and I would actually make a translation, I would say, okay, K actually refers not to momentums, but to space Euclidean coordinate. Yeah?
Right.
Then the Hamiltonian would actually be just the usual Hubbard.
Then that would just be the usual Hubbard model.
But there would be no hopping from one side to the other, right?
No, the Hamiltonian has a kinetic energy term.
No. In that case, the psi of K would be psi in direct space. So it would be more like an impurity potential that sets the energies apart.
No, but it's a four fermion term. I'm not sure I know what you're.
No. The four fermion term is the one with the U, right?
Yeah. So then, what do you want?
Like the U is on a side R up would interact with another electron on side R up. If I just make a transformation and say, okay, let's suppose that K refers to the coordinate space, then you would have a U on every side. But every side would have a different local energy given by psi of R. And so actually, if you look at it this way, then you would have an interaction that is completely local, but there is simply no hopping between sides. The only thing you have is sides having different side energies, and that's all. And then if I look at it this way, then I have a sort of a hard time understanding how any kind of conductivity, let alone superconductivity.
Okay, so I guess I don't quite understand your translation, because if I
Why is that? Oh, this is for bosons.
No. Sorry. Let me just say exactly what.
That's Fermi-liquid, right?
What if you interpret K as coordinate instead of momentum?
No, but if I do it, then I can much more easily understand what's actually happening, because you're simply.
So NK is CK dagger CK.
Yeah, sure, I know.
Okay.
Yeah.
Now, what do you want me to do?
I just want to say, well, it doesn't matter.
So this is the model that we solved.
Yeah, it's a
if you now want to go and say substitute I for K,
yeah.
That's the Hubbard model.
Yeah.
We didn't solve that model.
Well,
no one can solve that model.
No.
That's why we went to this model.
Yeah.
So what are you saying?
I'm saying if we just make life easy for ourselves, conceptually.
But that's wrong. I mean, I'm just telling you that that's wrong.
No, it doesn't matter. Yeah, for the model and for the mathematics, it really doesn't matter.
Well, yeah, it does, because the kinetic energy term then doesn't commute with that term.
I think we'll have a good chance to discuss this over here.
No, but the kinetic energy term doesn't commute with that.
No,
and then the model's not solvable.
You have to do that transformation for all terms, for both, of course, at the same time. But and then it doesn't matter. It's just the same. The math is exactly the same. The interpretation changes a bit.
Sri has a quick question.
I'll explain what is K. K is just a dummy variable here. Why can't you make K? K doesn't matter. You're summing over K. Why can't you make Ki? It's just a formal thing. I agree that K should not matter if this is the Hamiltonian. there's some other assumption that Philip is not Philip.
Okay, Sri.
Okay, so Philip, I have just a philosophical question. The minute